All right, chapter 10 is homework 20 and 21. Homework 20 here, we're going to start by sketching the least squares regression line. The least squares regression line is sometimes called the line of best fit. You want the line that goes through this data as closely as possible. You're just sketching, you're not finding it exactly, so all you're going to do is put a line through that data that goes somewhere close, so just your best guess is okay. And so in this case, I'm just going to start down here and I'm just going to make my line and go up through here, and it goes somewhere close to my data. So that's called the least squares regression line, or the line of best fit. And so here they had their bivariate data for the quantitative variables x and y in the table. They put all the points on the table for you, and you're just going to sketch the least squares regression line, or the line of best fit. So just whatever your best guess is, pretty easy to do. The line tool on Alex, you're just going to click in two spots, one on the bottom, one on the top, and it'll put that line through there for you. Number 2 then, my bivariate data for the quantitative variables x and y are given in my table below. Again, they plotted all the data for you. In the scatter plot, sketch an approximation for the least squares regression line, otherwise known as your line of best fit. And so you're just going to approximate it anywhere in there. This one in this case is going to go down. And if I had a straight line there, it'd be close to my line of best fit. So it doesn't have to be exact, just approximating where it is as close to the dots as you can to get a line that goes in the middle of your dots. Number 3 here, if I slide this up so we can see it. Again, our bivariate, that means there's 2 variables, an x and a y. For our quantitative variables are given in the table below. These data points are plotted in the scatter plot, so they've plotted all the points out for you. In your scatter plot, sketch your approximation for the least squares regression line. So my least squares regression line is my line of best fit. I'm just going to approximate a line that goes somewhere close to the middle of my data, and so it might look sort of like that. Four, 5, and 6, now we're doing the linear relationship and the sample correlation coefficient. The sample correlation coefficient is called R. It gives you a value, and if the value is 1, then my line would be exactly straight. If it's positive 1, my line would be going up. If it's negative 1, it's going down. And so when you do R, when you're doing statistics, R tells you how close to your line of best fit is to your dots. It's only equal to 1 if your dots would all be in an exact straight line. So on this one, my R value would be close to negative 1 because that's going downhill. On this one, again, my line is going to be close to positive 1 because it's going up. Here's my line going down, here's my line going up, but my dots aren't exactly straight. Here, you'll notice that my dots are scattered all over the place. I would be somewhere around 0 because there's no place that I could draw a line that would make sense to be a line of best fit on that one. This one, if you look at your dots are kind of going downhill, but they're scattered out more than your dots here. So this is a negative slope, but it's probably not very close to negative 1 because my dots aren't very close to my line. They're scattered all over the place. So answer the following question about the relationship between the pairs of variables and the values of the sample correlation coefficient, otherwise known as the R value. The same response may be correct for more than one question. Which data sets indicates the strongest negative linear relationship between the 2 variables? Well, we had 2 negative relationships. This one up here is the stronger relationship because it's closer to the line. And so what they're going to do is use the variables that are given in the table. So they're going to say that figure 1 where I do W to T, W2T, or W, no, that's not W to T. figure 1 where I do x to y is the one that is closest. So figure 1 does x to y, and that's the one that's closest to a negative linear relationship. The second one, for which data set is the sample correlation coefficient closest to 1? In this case, here is the one that's closest to positive 1. My slope is going upwards. So figure 2, which is the variables u and v, so they'll say u to v. Number 3, for which data set is the sample correlation coefficient r closest to 0? Closest to 0 is the one where my points are scattered out all over the place. Happens to be figure 3. They're putting these all right in a row. My variables on that one is the w to t. And on this one it says for which data set is the sample coefficient r equal to -1? If it was equal to -1, all my dots would have to be exactly straight on my line. In this case, it's close to -1, but not equal to -1. So my choice here is that none of them fit that answer. There are none that are exactly equal to -1. So number 5, below are 4 bivariate data sets and the scatter plots for each. Note that each scatter plot is displayed on the same scale. Each data set is made up of sample values drawn from a population. So in this case, this one has a positive slope. And it's close to +1. Again, it's not exactly +1 because it's not exactly straight. This one here, it's going to be close to 0. Because all my dots are scattered all over the place. There's nowhere I can draw my straight line. Here we go. This one, notice all my dots are exactly straight in a row and it's going positive. This one is exactly equal to 1. And on figure 4, here we have a negative slope. It's not really close to -1, but it is a negative slope. And so if we look here, it says which data set indicates the strongest positive linear relationship. The strongest positive linear relationship, both of these are positive, but the strongest one is when it's exactly equal to 1. So in this case, figure 3, which is doing w to t using my variables up here on my table. Number 2, for which data set is the sample correlation coefficient r equal to -1? I don't have any that's exactly equal to -1. I have one equal to +1, but nothing equal to -1, so I say none. This one is negative, but it's not an exact straight line. Which data set has a apparent positive but not perfect linear relationship between my two variables? So in this case, here's the one that's positive, but it's not perfect because it's not exactly equal to 1. It's close, but it's scattered around. So which one has a +1 but not perfect? Figure 1, which is x to y. And for which data set in the sample correlation coefficient r closest to 0? The one that's closest to 0 is the one where my points are scattered all over, which is figure 2. Figure 2, the variables there are u to v. U to v. Number 6. Here again, below are 4 bivariate data sets in the scatter plot for each. Note that each scatter plot is displayed on the same scale. Each data set is made up of sample values drawn from a population. So on this one, notice my dots are all in a straight line. My line is going downhill, so it's exactly equal to -1. It's -1. This one, if I drew my line of best fit, is negative. Didn't quite get that in there in the right spot, but it is negative, but it's not exactly equal to -1. This one, notice I have what has kind of looks like a parabola. It's a quadratic relationship. but it doesn't have a slope of a line that I can give you. And so in this case, I'm going to have to just say, oh, there's no positive or no negative relationship on that one. On this one, if I drew my line in here, again, my line would go positive. My dots are scattered all over, so it's not exactly equal to 1, but it does have a positive slope. So, for which data sets indicates a perfect positive linear relationship? Again, here, when I look at that, I don't have anything that's perfectly positive. I have one that's perfectly negative, and so I'm just going to say none. For which data set has an apparent positive but not perfect linear relationship? Here's the one that has a positive relationship, but it's not perfect, and so that's figure 4. Figure 4 says we have what variables there? I'm having a hard time reading that. M to N. That's what those say. M to N. In which data set is there evidence of a strong nonlinear relationship? Here we have that nonlinear relationship. It's not a line, it's a parabola is what it is. But there's not a linear relationship there at all. And so figure 3 has a nonlinear relationship. That's the W to T. And the last one, which data set indicates the strongest negative linear relationship? This one here that is perfectly negative has the strongest relationship. It's better than this one where my dots are scattered about around my line. So the one that has the strongest negative relationship, figure 1, which is X to Y. Can't remember on the drop down, they might just have the variables M to N instead of figure 4 and 3 and 1, but just in case, you'll know which ones I was talking about. All right. Number 7, 8, and 9, we're doing predictions from the least squares regression line. So y hat equals 8.45 minus 0.27x is your least squares regression line. This value right here, the one in front of the x, is the slope of your line. You can see that this line has a negative slope. That's the slope of my line. So what they have here is my table here. The well-known psychologist, Dr. Elbod, has established what he calls his generalized anxiety scale, GAS. The GAS score, which is a scale from 0 to 10, measures the general anxiety of an individual with a higher GAS score corresponding to more anxiety. Dr. Elbod's assessment of anxiety is based on a variety of measurements, both physiological and psychological. There we go. We're interested in making predictions about individual sleep behavior based on their GAS score. The Bivariate data below gives the GAS score, denoted by X, and the number of hours of sleep last night, denoted by Y. For each of the 15 adults in the study, the least squares regression line for the data has the equation y hat equals 8.45 minus 0.27x. This line, along with the scatter plot of the data, is shown below. So here they have the original data. That's the dots on my plot. Here they put in that line of best fit, that least squares regression line, and that's the equation of my line. So the first part says, fill in the blank. For these GAS scores that are greater than the mean of the GAS scores tend to be paired with sleep times that are blank than the mean of the sleep times. So when I do my means are my averages. What I do to figure out the mean is I just think about here is about the middle of my thing, here's about the middle of my thing. My x-axis, my horizontal axis, or my x scores would be the mean of my x scores, because that's the mean of my x-axis. Here would be the mean of my y scores. So we are going to figure out for the data scores that are greater than the mean of the GAS scores. The GAS scores are your x ones, and the y are your sleep times. So for these values here that are greater than the GAS scores, They tend to be, I better mark all of them here. All of these on this side. Those values that are greater than my GAS score tend to be greater or less than the mean of my sleep times. Well, the mean of my sleep times is this bar right here. Do I have more dots above the bar or more dots below the bar? In this case, I have more dots that are below the bar, and so they would be less than the mean of the sleep times. So my mean of my X is going to go vertical. The mean of my Y will go horizontal. So here I'm checking if I'm greater than my X, so everything on the right, where do I have more dots? Less than my Y. According to the regression equation, here's my regression equation. For an increase of 1 in GAS score, there is a corresponding decrease of how many hours in sleep. We use the slope of the line to figure out what the decrease is. In this case, we see that the slope is negative 0.27, which means it decreases by 0.27 for every 1 increase in X. Number 3, from the regression equation, what is the predicted sleep time in hours when the GAS score is 3? So what we're going to do is use our regression equation, put 3 in for X and calculate that. Y hat is equal to 8.45 minus 0.27 times 3. And so I'm going to go ahead. This one says round your answer to at least 1 decimal place. So take 8.45 minus 0.27 times 3. If you round that off to 1 decimal place, you should come up with somewhere around 7.6. 7.6. So that means exactly on my line, when X is equal to 3, I would be at 7.6 on my line. Number 4, what is the observed sleep time in hours when the GAS score is 3.0? So on this one, for the observed one, you're going to find it in the table. So in my table, I want to find the data point that has a GAS score of 3. The sleep time there then is exactly 7.0. So that one I can just pull right out of the table. Number 8 then. The managers of an electric utility wishes to examine the relationship between temperature and electricity used in the utility service region during the summer months. In particular, the manager wishes to be able to predict total electricity use for a day from a maximum temperature that day. The bivariate data given below gives the maximum temperature in degrees Fahrenheit and the electricity use in thousands of kilowatt hours of electricity generated and sold for a random sample of 16 summer days. A best fit line for the equation obtained from the least squares regression is given by y hat equals 57.99 plus 2.99x. So in this case, the slope of my line is the 2.99 in front of the x, in which x denotes the maximum temperature and y denotes the electricity use. This line is shown in the figure 1 scatter plot. So in my scatter plot, x is the temperature, the electricity use is the y. So again, this first question is going to talk about the mean. So the mean would be about halfway between. The mean of x is your temperature. The mean of y about halfway between here. The mean of y is going to be your electricity use. So for the data values for electricity use that are greater than the mean, so this time I'm doing greater than the mean of the electricity use, I'm doing the values that are above that mean line. For the values that are greater than the mean of the electricity use tend to be paired with temperatures that are greater than or less than the mean. So for my temperatures here, I want to look, do I have more dots above the line, or I shouldn't say that, more dots to the right or more dots to the left, because I'm looking this way, that's where my circle goes. If I look here, I have more dots over here on the right-hand side than I do on the left-hand side. So since I have more dots on the right, I'm going greater. So when my mean is greater for my electricity, my temperature is also going to be greater in this case. Number 2, fill in the blank according to the regression equation. For the increase of 1 degree Fahrenheit in temperature, there is a corresponding, and what they want you to pick here is, are you increasing or decreasing by 2.99 thousandths of kilowatt hours in my electricity use? So I look at my slope. My slope was 2.99. It's positive. Since my slope is positive, it's going to increase, right? My line is increasing with the more electricity that I use. What is the observed electricity use in thousands of kilowatt hours when the temperature is 98.3? So for the observed one, that's where we look it up in the table. 98.3 I have to find in my table. 98.3 is the second one from the top. And the corresponding value that goes with 98.3 then is 298.0. And then the fourth question there, from my regression equation, what is the predicted electricity use in thousands of kilowatt hours when the temperature is 98.3? So now they're going to have us use the equation. Y hat equals 57.99 plus 2.99x. I'm going to substitute in 98.3 for my x. So I'm going to do 57.99 plus 2.99 times my 98.3. Just plugging that into my regression equation. Again, we're rounding our answer to at least one decimal place. So if you take 57.99 plus 2.99 times my 98.3, I should come up with 351.9. 351.9. And number 9. The Cadet is a popular model of sport utility vehicle known for its relatively high resale value. The bivariate data given below were taken from the sample of 16 cadets, each bought new 2 years ago, and each sold within the past month. For each cadet in the sample, we have listed both the mileage, X, in thousands of miles, and the cadet had on its odometer at the time it was sold, used, and the price Y in thousands of dollars at which the cadet was sold, used, with the aim of predicting the used selling price from the number of miles driven. We might examine the linear square regression line, the line of best fit, as Y hat equals 41.09 minus 0.46x. This line is shown in the scatter plot of figure 1. So they're selling their used vehicle based on the mileage. What is the price that the person received? So in this case, again, fill in the blank. For these data used in the selling price that are greater than the mean of the used selling price tend to be paired with which mileages that are blank of the mean of the mileages. So again, vertical line is my X bar, my X is my mileage. Horizontal line, look for about the average or the middle. My Y bar is going to be my price. So, for the data, the used selling price that are greater than the mean. So, the ones that are greater than the mean, above my line, tend to be paired with mileages that are, so I'm looking at my mileages. Do I have more mileages to the left or to the right? We have more dots over here on the left side, so that means it's less than the mean of the mileages. If I were on the right, it'd be greater. On the left, it's less. Number 2 here. According to the regression equation, for an increase of 1,000 miles in cadet mileages, there's a corresponding decrease of how many thousands of dollars in the used selling price. So again, I'm looking at the slope of my line. Since my slope is negative, it is a decrease, and they tell me that in the problem. It is going to decrease by 0.46 then. So I'm using my slope to answer that question. From the regression equation, what is the predicted used selling price when the mileage is 39.2? So now I'm going to use my regression equation. Y hat equals 41.09 minus 0.46x. I am going to use 39.2 in for my x value. So I'm going to do 41.09 minus 0.46 times 39.2. Just plugging that value into my regression equation. I'm going to predict what it might be. So if I put that number in there, 41.09 minus 0.46 times 39.2, rounding to 1 decimal place, my answer would be 23.1. And number 4, they're also going to use your regression equation. So basically you're doing the exact same for number 3. From the regression equation, what is the predicted used selling price in thousands of dollars when the mileage is 21.8? So now we're going to use our regression equation, 4.09. Woo. Stop writing on me for a minute. Doesn't want me to write. Well, let me do this. It'll write in red, but it should write. There we go. 41.09 minus 0.46 times my value here, 21.8. And so if you take the 41.09 minus 0.46 times 21.8, again, we're rounding this off to 1 decimal place. I'll try to make that look like it's in red like the rest of it. 41.09 minus 0.46 times 21.8 should give you 31.1 for my predicted value using my regression equation. So this one didn't ask you for any observed ones from the table. Both of them were predictions from my regression equation, and I just plug my number in and solve. All right. Computing the sample correlation coefficient and the coefficients for the least squares regression line. So these ones here, you're going to have the problem 2 different ways. Either you're going to calculate the sample correlation coefficient, which is R, or you're going to do the coefficients for the least square regression line, which means you'll be writing the equation y hat equals and figuring out what the equation is. So on this first one here, it says Sir Francis Galton in the late 1800s was first to introduce the statistical concept of regression and correlation. He studied the relationships between pairs of variables such as the size of the parents and the size of their offspring. Data similar to that which he studied are given below, with the variable x denoting the height in centimeters of a human father and the variable y denoting the height at maturity in centimeters of the father's oldest son. The data are given in the tabular form and also displayed in figure 1 as a scatter plot. Also given are the products of the heights of the fathers and the heights of the sons for each of the 16 pairs. These products written in column labeled XY may aid in your calculation. They will in your calculation because you need to have them. So they're not going to make you take the 175.3 times the 176.7. They already did that for you. However, you do need some data from this table. So we are going to use our calculator in order to figure out that data. So again, we're going to just use our statistics, and what we have to do is calculate the mean and standard deviation, etc. of the first column and of the second column. Now you can either put all your values into list 1 and then the other set of values into list 2, or you can put them in list 1, calculate your statistics, then go back and put the other one in list 1, calculate your statistics, and go from there. So, if you again hit Stat, 1 for edit, and cursor up and clear out whatever's in there, hit Enter. If you list all of the heights of the father in list 1, You could also do the sums in list 2 if you wanted to, but then you'd have to calculate your statistics on list 2. Otherwise, like I said, just put all of these in list 1, calculate your statistics, then we'll do all of those in list 1 a second time, do the second ones, calculate your statistics, and we'll go from there. So go ahead, pause the recording for just a bit while you get your data in there and calculate on there your mean and your standard deviation, the S of X. So you're going to want the X bar for the first list, the S of X for the first list, and then we're going to do the second list. So X bar for the second list and S of X for the second list. I've already done the calculations, but go ahead, pause the video, put them in there, figure out your data, and when you're ready, you can double check with what I got here. So X bar of 1, when I did the first list, I'm going to say that was list 1. Almost looks like list 1. I got a mean of 180.5. And my standard deviation, my S of X, was 13.7125. In this case, N1, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have 16 numbers. When I did my second list, you can either put them in list 2 or just re-put them in list 1 and calculate your statistics again. Doing the calculations on list 2, my mean of list 2 was 181.544 if I round that off. We need to carry, to 4 decimal places. I better go to 4 decimal places. Carry my intermediate calculations to 4 decimal places, it says on this one. So 181.5438. My standard deviation, 8.9416. So again, can't get that right. 8.9416. We're just going to use the stat, do 1 to edit, and then you're going to do stat, and you're going to calculate number 1 for 1 variable statistics on your list. So find that information. We'll need it in our formula. The other thing you need to do in order to figure out the answer to this problem is you need to find the sum of your XY column. So here's my symbol for sum. It looks something like that, the sum of XY. So you'll want to go through and add all the numbers up that are in your XY column. Again, go ahead and just pause the video, add them all up. I already have done it, so I'm not going to wait a whole bunch of time for you to do your adding. But if you add all those numbers in the XY column, finding the sum of this column, you should come up with 525817.49. So 525,817.49. So adding all the sum here gets the sum of that. So once I have that information, I can then use the formula to find what my R value, my sample correlation coefficient is. What this number stands for is when I do my line of best fit, how close is that data to my line? If it was exactly on my line, I would get an R value of 1. You can see here I'm not exactly on the line, so my R value is going to be probably somewhere close to 1, but not going to be exactly 1. We're going to find out what it is. So the formula says to do the sum of XY, which is this number right here that we just found, minus N times the mean of X1 and the mean of X2. 2 over n minus 1 times the standard deviation of x1 and the standard deviation of x2. So the n's for both of these should both be 16 because I have the same numbers, father and sons, they both were 16. So I'm going to plug that into my formula, do my calculations. So I'm going to take 525,817.49 minus n was 16 times the 180.5 times, I'll sneak it down there, the 181.5438. I'm writing it sideways. So on the top of my fraction, I have the sum of xy minus n, which was 16, times the mean of my first set of data, which was 180.5, times the mean of my second set of data, which was 181.5438. That all is on the top of my fraction that I didn't leave myself enough room to write. Then I'm going to do n minus 1. So I am going to do 16 minus 1 times the standard deviation of the first, which is the 13.7125, times the standard deviation of the second, which is the 8.9416. You can almost read all of that. I don't have any spots that are any whiter to write on. So, again, you're going to punch this into your calculator. The Alex calculator is probably easier to punch it into. Or find the top number, then find the bottom number, and then go ahead and just divide your two numbers. But the sum of this column xy, then the number of items we have, the mean of the first, the mean of the second, and that's your list 1 and your list 2. Then n minus 1, the standard deviation of the first and the standard deviation of the second. When you work that out, you are going to go to 3 decimal places. Again, I may have rounded off a little differently than you, but you should be close to 0.826. 0.826. The closer you are to 1, the closer you are to having all those dots line up in a nice straight line. You can see that they're not quite on the line, but they are pretty close in my positive direction. So 0.826 is the value of R. So put list 1 in your calculator, find your statistics. List 2 in your calculator, find your statistics. Add up all the values in the XY column, and then you can plug them into your formula. All right, number 11. Number 11 says an electric utility wishes to examine the relationship between temperature and electricity use in its service region during the summer months. The bivariate data below give the maximum temperature, denoted by X in degrees Fahrenheit, and the electricity use, denoted by Y in thousands of kilowatt hours, for a random sample of 15 summer days. The data are shown in figure 1 in the scatter plot. The value of the sample correlation coefficient is approximately 0.707. So R is 0.707. If I would put my line of best fit in there, you can see my data scattered out farther from my line, so it's farther from 1. Answer the following. Carry your intermediate computations to at least 4 decimal places and round your answers as specified below. So first of all, they're going to have us find the value of the slope for our least squares regression line. So again, we're going to do our regression line y hat equals, and first of all, we're going to find the slope of that value, which is the number in front of the x. So in order to find the slope of that value, they're going to tell you that we're going to do y hat equals b sub 1x plus b sub 0. The b sub 1 is the value of your slope. So the formula to find that value for b sub 1 is to do R times the standard deviation of your X column over the standard deviation, oops, I better do that the right way. Standard deviation of your Y column is on top. Standard deviation of your Y column over your standard deviation of your X column. So again, you're going to have to use your graphing calculator. Do your X column and find your statistics. Do your Y column and find your statistics. Go ahead, pause the video while you type those into your calculator in order to find your data. I've already calculated it out. So again, I'm going to have my list 1, which I'm going to call my X bar for my mean, my list 2, my Y column for my mean. And so separately, I put in my data for list 1, calculated the statistics on that list. My mean was 85.2800, going to 4 decimal places. My standard deviation, 9.9369. And if I counted here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 numbers on my list, so N is 15. Then I did my data in my second column, my Y column. If I do my data in my Y column, I'm going to have a mean of 314.1933. I'm going to have a standard deviation of 39.8793. So put those in your calculator in the stat function in your list. Calculate that out. Again, you do stat and 1 to edit to put your list in, and then stat and go to calc and 1 for the 1 variable statistics. Now that I have that data, I can use my formula to find my B1 value. B1 is equal to the R value, 0.707, times my standard deviation from my Y, 39.8793, divided by the standard deviation of my X, 9.9369. Go ahead, punch that into the Alex calculator, 0.707 times 39.8793 divided by 9.9369. If you do that calculation, we are rounding this one to 2 decimal places. You should come up with 2.84. 2.84. That would be the slope of your linear regression line. So y hat would equal 2.84x. Now you're going to find the value for the b sub 0. The b sub 0 is your y-intercept of that line. It tells us the formula to find b sub 0, I'm going to write it over here, is the mean of y minus b1, which is your slope, times the mean of x. So in order to calculate that out, I'm going to write it down here, b sub 0 equals the mean of y, 314.1933, minus the b1 value, which is your 2.84, times, I'll put it underneath there, but it's really behind there, the mean of x, which is the 85.2800. I'm going to write that over here again. B sub 0 equals 314.1933 minus 2.84 times 85.2800. There, now I got it all the way across the page so you can see how that should be typed in. I'm going to go ahead again. You could put that in your regular calculator or use your Alex calculator. But the mean of y minus the 2.84, which was your slope, times the mean of x. When you put that into your calculator, you should get 72.00, 72.00. That means that on the end of my equation, I would have that, and that would be my line of best fit. Or the equation of my line of best fit looks something like that. So two parts to that. You're going to find the slope by taking r times the standard deviation of y divided by the standard deviation of x. And then you're going to find your y-intercept by taking the mean of y minus the slope times the mean of x. And last one on this page. Let's see if I can get the whole question there. It says, the well-known psychologist Dr. Elbot has established what he calls his General Anxiety Scale, GAS. The GAS, which is a scale from 0 to 10, measures the general anxiety of an individual, with higher GAS scores corresponding to more anxiety. Dr. Elbot's assessment of anxiety is based on a variety of measurements, both physiological and psychological. We're interested in making predictions about the individual's sleep behavior based on their GAS scores. The bivariate data below gives the GAS score denoted by X, and the number of hours of sleep last night denoted by Y for each of the 15 adults participating in the study. A scatter plot of my data is shown. So in this case, if I would put my line of best fit in there, it would look something sort of like that. So this one, although it tells you to find the y-intercept first and the sample correlation coefficient, in order to find the y-intercept, you also have to find the slope, because that was part of my equation. So I am going to go ahead and find both the B1 so that I can find the B0. So even though it just asked for the y-intercept, you have to find the slope and then find the y-intercept. So again, on this one, you will use your calculator, the stat function, put list 1 in and find your statistics, put list 2 and find your statistics. Again, just pause the video while you're putting that data in and finding those statistics. When you're done, turn it back on. I have already calculated them. So stat function, 1 for edit to put your list in, and then stat, calc, and do the one variable statistics. So on my list 1, my x values, x bar, my mean came out to be 5.2133. My standard deviation for that first list, 2.7640. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So n is 15. When I did my second list, the y list, the mean of y came out to be 7.0267, and the standard deviation of y, 1.0606. So, we don't have to find the slope if I would have read the problem. The least square regression line for this data has a slope. They gave us the slope, so we don't have to find the slope. So we know that in our equation, the B1 value is your slope, is negative 0.27. So they did give us that. We don't have to calculate it out. So since we do know what the slope is, we can then go to the formula to find out what B0 is. B0, we said, was the mean of y minus the slope, which is B1, times the mean of x. So in this case, my mean of y, 7.0267. I'm going to subtract the slope. In this case, my slope is negative. So I'm going to subtract a negative 0.27 times my mean of x, 5.2133. So be careful on that. there's a subtraction in the formula, and then our slope is negative, so I'm going to have minus and then a negative 0.27 times 5.2133. So again, just put that in your calculator, 7.0267 minus parentheses negative 0.27 parentheses 5.2133, and rounding that off to the nearest hundredth or to 2 decimal places, we would have 8.43. Which means my regression equation would have been y hat equals negative 0.27x. My slope is negative with a y-intercept of positive 8.43. You can see I kind of drew my line in there. It's not quite at 8.43, but it's kind of close to that. It's between the 8 and the 9 anyway, so when I drew my line in there, it was kind of close. On the second one, we want to find that sample correlation coefficient. And so in order to find your sample correlation coefficient, we're using the formula that R is equal to B1 times the standard deviation of X divided by the standard deviation of Y. So in this case then, R is going to equal B1. B1 is my slope that they gave me, negative 0.27. This one formula has the standard deviation of X on the top, 2.7640. And it has standard deviation of Y on the bottom, 1.0606. And so, a lot easier to find your R value if you know that information from your equation instead of having to use that gigantic formula we used on the first problem. We're just going to punch that into our calculator. So negative 0.27 times 2.7640 over 1.0606. Rounding off to 3 decimal places on this one, we should get negative 0.704. And again, depending on rounding, it may be different, but I did carry mine to 4 decimal places like they specified, so I should be pretty close. All right, that is the end of homework 20.